Imagine a bustling city that never sleeps, where factories continuously churn and pollution steadily accumulates. This city resembles a cancer cell, hyperactive, voracious for nutrients, and constantly generating waste products, including harmful molecules known as reactive oxygen species, ROS. These molecules are unstable and can damage cells, much like pollution damages a city. Cancer cells, surprisingly, embrace these molecules because they help fuel their rapid growth. But there's another player in this busy cellular city, iron. Iron, while essential to many normal bodily functions, behaves like a double-edged sword. Unlike healthy cells, cancer cells are greedy. They accumulate vast amounts of iron, much more than their normal counterparts. However, this iron can lead to trouble. In fact, having too much iron makes cancer cells vulnerable to a particular kind of self-destruction called ferroptosis, a form of cell death triggered by excessive iron-driven oxidative stress. Researchers have noticed this weakness and are exploring ingenious ways to exploit it. For example, using a technology called non-thermal plasma, scientists can break down ferritin, the protein that safely stores iron, in cancer cells, releasing more free iron. This free iron generates toxic molecules that rip apart cancer cell membranes, leading to ferroptosis. Another promising compound, FiNO2, directly interacts with iron to cause harmful oxidation, pushing cancer cells further toward ferroptosis. Researchers also found that certain genes, when silenced, reduce a cancer cell's ability to export iron, effectively trapping it inside the cell and hastening its demise. In lung cancers, suppressing an enzyme called NFS1, vital for iron balance, pushes cancer cells toward starvation of usable iron. Desperate, these cells accumulate more iron and fatally trigger ferroptosis. Interestingly, certain natural compounds are potent ferroptosis inducers. Selenomycin, for example, traps iron inside specialized structures called lysosomes, causing these tiny storage bins to burst, effectively killing stubborn cancer stem cells. Likewise, with afrin A derived from traditional medicinal herbs, disrupts antioxidant defenses and indirectly increases free iron within neuroblastoma cancer cells, forcing them into ferroptosis. Cancer cells, aware of their toxic internal environment, boost their antioxidant defenses to survive. One key antioxidant molecule they depend upon is called glutathione, GSH, managed by a protein known as GPX4. Inhibiting GPX4 is proving to be a strategic move because cancer cells that have undergone a process called epithelial to mesenchymal transition, EMT, which makes them resistant to many conventional treatments, are especially dependent on GPX4. Disabling GPX4 therefore exposes these aggressive, drug-resistant cancer cells to ferroptosis. Ferroptosis also holds promise for tackling metastasis, the spread of cancer cells throughout the body. Melanoma cells that travel via the bloodstream need resistance against ferroptosis to survive the harsh journey. Researchers discovered that blocking ferroptosis actually helps these melanoma cells spread. Thus, promoting ferroptosis could effectively reduce metastasis. What's even more fascinating is ferroptosis' connection with our immune system. Our immune cells can actually trigger ferroptosis to kill cancer cells. Specifically, CD8 plus T cells, part of our immune defense, produce molecules that block cancer cells' antioxidant supply, pushing them toward ferroptosis. Enhancing ferroptosis alongside immunotherapy may prove especially effective, making tumors more vulnerable to our body's natural defenses. Ferroptosis is also making waves in enhancing radiation therapy. Radiation damages cancer cells and can trigger ferroptosis by promoting lipid oxidation and iron accumulation. Certain clinical drugs, from common medications like ibuprofen to potent chemotherapy agents such as cisplatin, have also been shown to induce ferroptosis, greatly boosting their effectiveness against tumors. The cutting edge of this research lies in nanotechnology. Tiny nanoparticles, smaller than the width of a human hair, are now designed specifically to induce ferroptosis within tumors. These nanoparticles deliver iron, disrupt antioxidants, and even harness light to initiate ferroptosis. This approach has already demonstrated exciting results in animal models. Although much of this research is still in early stages, ferroptosis presents a groundbreaking strategy in cancer treatment. Exploiting cancer cells' iron dependency could revolutionize therapy, overcoming resistance to current treatments, and harnessing our own immune system to fight cancer. In this new chapter of cancer therapy, ferroptosis might become a powerful tool, finally tipping the scales in humanity's favor in our long battle against cancer.